Hello, in this video we study sequences. We learn how to find the limit of a sequence. And we're talking about conversions and diversions of sequences. This is a foundation for the next topic series. So I hope that we learn this topic well. Firstly, let's consider some examples about sequences. Okay, so we know, for example, if you have xn, that is kind of negative 1 to the n, right, where n is natural numbers 1 2 3 and so on. So you have a sequence of numbers. For example, x1 is equal to negative 1 2 to 1, which is negative 1, right? X2 is negative 1 square, which is 1. And then you plug x3 n equal to 3 into this, you get negative 1 cube equal to negative 1, and so on. So you may write this sequence as, I write like this, xn equal to negative 1, 1, negative 1, 1, and so on. Does that make sense? Where the number xn equal to negative 1 to the n is general term of this sequence. Okay, so let's talk about the second example. Sometimes we denote by an. That's fine. An, xn, or yn. It does not matter. Okay, 3 plus negative 1 to the n, where n is natural numbers, right? 1, 2, 3, and so on. So we can find some first terms of this sequence. Let's say a1. What is a1? 3 plus negative 1, 1. Here you get 3 minus 1 is 2. So that's the first term. Okay. If you want to find a2, you plug 2 into this formula. You get 3. Negative 1 squared, you get 3 plus 1 is 4. You want to find a3, you plug 3 into the formula, right? You get 3 minus 1 equal to 2, and so on. And again, this is the general term of sequence. So, sometimes people might give you, they might give this sequence as follows. Okay, they have an, it's just 2, 4, 2, 4, and so on, right? And of course, they don't give us the general term in here. Sometimes we need to guess the general term. Does that make sense? Sometimes we need to generalize these numbers and find the rule. Okay, that means find the general term of that sequence. Agree? All right, let's consider another example before we move to definition of sequence. So let's say I have an equal to n over 1 minus 2n, bn equal to n squared over 2 to the n minus 1, and so on. We have a lot of examples of sequences. All right. Now, if we talk about definition for sequences, so you would think we may define a sequence using functions. Look at this. For example, right here, you have some an, right? An equal to 3 plus negative 1 to the n. So if you look at this, the right-hand side part, that is just a function of n. Is that correct? It's a function of n. So they give you one value of n. You plug n into the function. You get the function value, which is an. But in this case, we consider the domain, which is natural numbers, n, the set of all natural numbers. So we might think about sequence that is a function of n, where n is in the set of natural numbers. Okay, so I can write like this. An equal to f of n. So, that is analytical definition of sequences. All right. So now, a sequence may be considered as a function. And from calculus 1, we know, if you have function, so you might need to consider the limit of the function, right? The limit of the function when n approaches infinity. So this is the limit at infinity. Does that make sense? So this limit, if you write that as an, so that's nothing but, limit of an approach infinity. If this limit exists, you say that the sequence an converges. If this limit is equal to infinity or does not exist, you say an diverges. Does that make sense? All right, so we have conversion diversion here. If the limit exists, then an converges. Okay, if the limit does not exist, we can say an diverges. I have to correct one thing. So we're saying here, if the limit exists, so the limit may be finite or infinite. Okay, so infinite is okay. Yeah, we still have, limit. I'm sorry for that. So we define the limit of a sequence using limit of functions, because a sequence can be considered as a function, right? And that function is defined on the set of all natural numbers. Let's consider the following example. I think we might use the previous one here. For example, an equal to -1 to the n. So we have seen that, this sequence is just -1, 1, -1, 1, and so on. So that means the corresponding function, an equal to f of n, which is -1 to the n. This function takes values, just -1 and 1. And of course, you can see that the limit of this function when n approaches infinity does not exist, right? Because that's just changed from 1 to -1, 1 to -1. Does that make sense? So the graph of this function look like this. So you have -1 in here and then 1 in here. If n equal to 0, you have 1, the first point, and then when n equal to 1, you get -1, you go back to this, and then you go to this, and then you go to this. You see, the function just changed, right, from time to time. So and text value only 1 and -1. So the limit does not exist. So that means an does not have limit. An diverges, right? That's an diverges. Does that make sense? Very similar example when you consider an equal to 3 plus -1 to the n. So you remember that we already wrote very carefully here. That sequence contains only 2 and 4, right? So when n is even, that is for even, n is even, right? And equal to 2 when n is odd. You see that? So again, this sequence diverges. Does that make sense? All right. Let's consider the function an equal to n over 1 minus 2n. Look at this. So that is your function f of n, right? What is the limit of f of n when n approaches infinity? We learned this from calculus 1. So limit at infinity, right? Uh, and in here we use similarity because when n approaches infinity, such coefficient does not affect on the conversions. Does that make sense? So you can ignore that because constant does not affect on this. So you may write in this case the limit is equal to n over negative 2n, and n approaches infinity, which is negative 1 over 2. So in this case you write limit of an when n approaches infinity equal to limit of f of n when n approaches infinity, and that is negative 1 over 2. Does that make sense? So see again, right? Very first topic of calculus 1. Very first topic of calculus 1. And then we need to use that right here. Limit at infinity. All right? We still have one more example in here. Let's say n squared over 2n minus 1. This is also a typical example, so I want to work right now. Limit of n squared over 2n plus 1 when n approaches infinity. Okay, so I write an in this case n squared over 2n plus 1. So, some students may have difficulty to find the corresponding function. And we need that in the future, not only in this section. When we study series and integrals, we need this. So the corresponding function fn en squared over 2n plus 1. Or sometimes you write f of x is equal to x squared over 2 to the x plus 1. Does that make sense? So if you want to find the limit of this of this sequence, so that means you have to find the limit of this function when x approaches infinity. Is that correct? So I can write like this. No, I write in the x language, right? Okay. X squared over 2 to the x plus 1. X approaches infinity. I would say this, right? Sometimes these two limits are different because in the first limit, n takes value only in the set of natural numbers. But if you write the limit like this, right? So that means x takes arbitrary value, not only natural numbers. But if two limits exist, then they should be equal. Does that make sense? And if this limit does not exist, so you might do conclusion that this limit does not exist. Agree? All right, so now let's consider the limit, this limit. When we study integration, improper integrals, let's remind you about this. Improper integrals. We study comparisons. Right? We study comparisons. And we say that we compare three types of functions. The first one is ln of x. The second one is x to the p or x to the n, whatever you want. The next one is exponential function, a to the x. Of course, we know that, polynomials approach infinity faster than logarithmic function. But at the same time, polynomial is slower than exponential functions at infinity. So that means, exponential function approach infinity faster than any polynomial. Does that make sense? Based on this observation, you would see right away the limit of this function is just 0. Because on the top you have x squared, in the bottom you have exponential function a to the x. In this case, yeah, a is greater than 1. Sorry, we need that condition. Otherwise, no, this just converts to 0. So if you remember this comparison and you write that, yeah, we have this comparison at infinity, and in this case, a is 2. So the limit is 0. From here, I can write the limit of an when n approaches infinity is equal to 0. I hope it is clear enough. Now let's consider some properties of limits of sequences. Since we define limit of a sequence using functions, so limits of sequences satisfy all properties of limits of functions. Suppose that you have two limits in here, two sequences in here, an and bn, and their limits are l and k respectively. So you would think about, yeah, for an you have some function f of x, right? For bn you have another function g of x, and the limit of f and g at infinity are l and k. So, all these properties are satisfied. Does that make sense? Because, that is just a very simple consequence of properties of functions, right? Of limits of functions. Now let's consider some examples in here. We reconsider the following limit. Limit of n squared over 2n plus 1. N approaches infinity. Of course, in this case, an is n squared 2 to the n plus 1, and f of x is x squared over 2 to the x plus 1. So we solve this limit, right? We saw that this limit equal to 0 using comparison, right? But again, in this example, we will show that the limit is equal to 0 using L'Hopital rule. Okay, we know that. We know this rule already. So let me remind this. If you consider the limit f of x over g of x, and you consider limit s of x0, okay, and if this limit has the form 0 over 0 or infinity over infinity, that means when you plug x0 into these functions, right, you get 0 over 0, infinity over infinity. So you might need to consider the following limit, the limit of derivative of f divided by derivative of g. Don't forget, this is not quotient rule. This is just quotient of derivatives. Okay? If the limit of this guy is x, then the limit of f of x over g of x approaches x0 equal to the limit of f derivative of x over g derivative of x. Okay? I repeat again, right? This is not the quotient rule. Okay? So, look at this. This situation happens so often when you consider limits of sequences. For example, in this example, you plug infinity, right, into this function. You get infinity over infinity. You see that? So, of course, this function, okay, you plug infinity to this, to f of x. You get infinity over infinity. So that means in this case, we may use L'Hopital rule. I will consider the limit, the derivative of the function x squared in here, and then the derivative of 2 to the x plus 1 when x approaches infinity. So this is what? This is the limit of 2x on the top, and here you have 2x ln of 2, x approaches infinity. And again, this limit still has the form infinity over infinity at infinity. So you differentiate one more time. You consider the limit of 2x derivative over 2x, 2 to the x, ln of 2 derivative. And this is equal to the limit of 2, because on the top, derivative of 2x is just 2, right? And here you have 2 to the x, ln of 2 times ln of 2. X approaches infinity. And of course, this is 0, because on the top you have constant. So, since the limit of this guy is 0, by the L'Hopital rule, the limit of this guy also 0. Since the limit of this guy is equal to 0, right? The limit of this guy is 0. By the L'Hopital rule, you get the limit of the original one is also 0. Does that make sense? So you have to apply L'Hopital rules twice. But again, right? If you remember the comparison, yeah, please use the comparison between exponential function and polynomials. Does that make sense? So according to the comparison, you have even, n to 2000 n and 20 over 2 to the n plus 1. This limit is still 0. And if you want to use L'Hopital rule, you have to differentiate. You have to apply the L'Hopital rule 2020 times. Does that make sense? But if you apply comparison between polynomials and exponential function, so you can get the answer right away. As we know, exponential function is faster than any polynomials at infinity. All right? And one more technique to find limits of sequences is the squeeze theorem. And that is also from topic of limit. The squeeze theorem. So remember that if you have two functions and now you have two sequence an and bn, okay, they have the same limit at, of course, at infinity. And suppose that an less than or equal to cn less than or equal to bn, then the limit of cn is also equal to L. Right? That is the squeeze theorem for sequences. You remember, if you have the limit of function f, the limit of function g, and here you have f of x less than or equal to h of x less than or equal to g of x, where h of x is the corresponding function for cn, right? Then by the squeeze theorem for functions, the limit of hx at infinity is also equal to the limit of f and g at infinity. That's it. It's very simple. Right? Let's consider some example. So we have sequence cn equal to -1 to the n times 1 over n factorial, where n factorial is product of the first n numbers. So we have that. We need to find the limit of this sequence. Okay, so this sequence is different to previous one because you have -1 to n in here, right? So the terms of this sequence may be negative, may be positive. Does that make sense? But from the definition of this sequence, we know exactly 1 over n to n factorial. The limit of this guy is 0. Because when n increase to infinity, 1 divided by n factorial decrease to 0. Agree? And when you multiply by -1 to the n, -1 to the n is bounded. This guy is bounded. You just take values, 1 and -1, right? So this is bounded. So that reminds you about the squeeze theorem. You have some bounded in here, right? And then you multiply with some guy, this guy converts to 0. So you take just two endpoints in here, and then that everything converts to the same point, which is 0. So let's apply the squeeze theorem. Okay, so I write the following one. 1 over n factorial -1 to the n, that is less than or equal to 1 over n factorial n greater than or equal to -1 over n factorial. You see? And the limit of 1 over n factorial n approaches infinity is equal to 0. From here, we have limit of Cn n approaches infinity is just 0. This is a very typical example of the following theorem, which is called the absolute value theorem. It says if you have some sequence an and the limit of absolute of an equal to 0, then the limit of the current sequence an also equal to 0. So this can be proved using the Squeeze theorem. Okay, so next time when you see something like this, right, okay, in this case, the absolute of Cn is 1 over n factorial, and the limit of 1 over n factorial is 0. So the limit of Cn is also 0. Does that make sense? So now I can write the limit of absolute of -1 to the n, 1 over n factorial, and approaching infinity is limit of 1 over n factorial and approaches infinity, and that is just 0. Don't forget, when you apply absolute, absolute of -1 to the n is just 1. Does that make sense? Then from here, you can do conclusion that the limit of -1 to the n over n factorial and infinity equal to 0 by the absolute value theorem. Okay? So I think we already considered enough examples. Now let's move to the next one, very, very important type of sequences, which is called monotonic sequences and bounded sequences. They have very, very interesting properties. Okay, sequences and bounded sequences. So suppose that you have some limit, some sequence an, okay? Let an is some sequence, and then the corresponding function for an is, I write fx is, I would write here representing, right, function for an. That means an equal to f of n. Okay. If the function fn is monotonic, I mean increasingly monotonic, then the sequence is also increasingly monotonic. If fn is decreasing function, so an is also decreasing sequence. Does that make sense? So that is one definition of monotonic sequences. Does that make sense? So I can write here and then we write another definition, right? So if f of x is monotonic, then fn is also monotonic. So you have two kinds of, monotonicity I write here, okay? But I write in the language of sequences. Let's consider definition. So an, the sequence an is increasing if an less than or equal to n plus 1 for any n to 1, 2, and so on. So that means, when you increase n, the function values just increase, right? Or we can write here, f of n less than or equal to f of n plus 1. Does that make sense? For any value n. and an is decreasing. I write here is decreasing if we have the another direction of inequality, an plus 1. For any n equal to 1, 2, and so on. So that means, the function f of x, so you have f of n in here greater than or equal to f of n plus 1. This function is decreasing, right? I mean, in terms of n, right? Does that make sense? That means when you increase the number n, the index n, the value an plus 1 is just smaller or equal to the value of the previous an. All right? So those sequences are very important. I would say that it's very important. Agree? Because for such sequences, if those sequences are bounded, that means they are bounded above or below. So such sequences might have limits. Does that make sense? All right. Let's consider one example. We want to see how to prove that a sequence is increasing or decreasing. Okay, so you might use this definition, or you might use the corresponding function. Look at this. You have, let's consider the function f x equal to 2x over 1 plus x. So the corresponding sequence would be an equal to 2n over 1 plus n, right? We want to see if an is increasing or decreasing. I will consider the function f of x. Let's differentiate the function f of x. Okay, we have f derivative equal to, we use the quotient rule in here, 2 times 1 plus x minus 2x times 1 divided by 1 x plus 1 squared. And we simplify this, we get 2 over x plus 1 squared. The derivative is always positive. So what does it mean? The derivative is positive means the function is increasing. Right? That's what we learned in calculus 1. And this increasing on the whole point, right? So if the function is increasing, that means the sequence is also increasing. Okay, so we use this all the time, don't forget that. We want to check if the function is increasing or decreasing. Yeah, we say, we take the derivative, we check the sign of the derivative. And then if the function is increasing, so the corresponding sequence is also increasing. All right, for sequences, that is for functions, right? For sequences, you might have the following picture. The sequence may be decreasing here, but from some value, the sequence is just keep increasing and increasing. And for the limit of sequence, we are interested in the limit when n approaches infinity. Does that make sense? So usually this interval does not affect the convergence of the sequence. Don't forget that. That is the difference between sequences and functions. Does that make sense? Okay, you look at sequences as a function, but you are interested in the function at infinity. Don't forget that. So you might ignore any finite intervals in here if you just need to consider convergence of that sequence. All right? Let's consider another example. I will choose the following one. Okay, let's start from an, okay? An is equal to 2 minus 2 over n minus 1 over n squared. So it's more complicated, right? But it's fine. The function f of x is equal to 2 minus 2 over x minus 1 over x squared. All right, let's differentiate this function. We see that f of x prime, 2 derivative is 0. So I will use, I write x to negative 1, and then I differentiate, okay? Minus x to negative 2, and I differentiate. I will get negative 2 times negative 1 x to negative 2 minus negative 2 x to negative 3. So I write that is 2 over x squared plus 2 over x cubed. And this is greater than equal to greater than 0 for x greater than 0. Because, we consider natural numbers, right? All values of x are positive. So the function is increasing. That means the sequence is also increasing. Does that make sense? All right, now this is very good. As I said, sometimes we may use this property to see if the limit exists or not. Okay, so this sequence has another very good property. This sequence is bounded. Okay, I write here the sequence a to the n is bounded. And of course, in this case, the upper bound is 2, right? Why? Because, an is equal to 2 minus 1 over n minus 1 over n squared. This is less than or equal to 2. Because these values are positive. So you subtract from 2 those positive numbers. So that should be less than or equal to, even here, strictly less than 2. So look at this picture. Here is 2, right? Y equal to 2. Here is infinity. So I hope you still remember horizontal tangent line. Horizontal tangent, horizontal asymptote. So when n approaches infinity, you have some, when n equal to 1, the function is 0, which is good. So the function keep increasing, and then, never attains to 2. In this case, y equal to 2 is the horizontal asymptote for the function f of x equal to 2 minus 1 over x minus 1 over x squared. Because the limit of f of x at infinity is 2. Is that correct? So, of course, in that case, the limit of sequence also exists and equal to 2. But in case, if you know exactly that the sequence is increasing and bounded, and that has upper bound, right? So we know exactly the limit of that sequence exists. Does that make sense? Okay, let me write that in here. If an is increasing, and bounded above, right? Then the limit of an and approach infinity exists. Okay, in case if an, oh wait, I think I do wrong here. I mean, and actually we have to reformulate this, and the sequence is increasing and has upper bound. Okay, let's say that. Okay, then the limit is x. If an is decreasing and has a lower bound, then the limit of an is x. So the low bound is almost similar to this. So you have a low bound here, and then the limit look like this. The graph look like that. Does that make sense? in order to finish this video, let's consider 3 more examples, and we see some sequences which are monotonic but not bounded. Some sequences are bounded but not monotonic, and some sequences satisfies both conditions. Okay, so the first example in here, 1 over n, the corresponding function is f of x equal to 1 over x, and we know that this function is decreasing because the derivative is equal to negative 1 over x squared. So this is monotonic, right? Is it correct? And not only that, I will write here increasing. Okay, and the function 1 over x is bounded because this is always less than or equal to 1. So the limit is x. And this is very easy, right? The limit of an equal to 0. Okay, this case, I write here the limit of 1 over n and approaches infinity is just 0. So we know that from calculus 1. All right, the second example, your function f of x is equal to negative 1 to the x, right? Of course, in this case, x is bigger than 0. And you can see that in the very beginning of this video, right? You have an just text value in the set of 1n and 1. Of course, this is bounded, but not monotonic. Okay, so and of course that is not it is not implies that the sequence does not have limit. No, we don't have that implication. But this is just a good example of say that this is not bounded and not it is bounded but not monotonic. And in this case, the limit does not exist. Okay, I repeat again, right? From here, it does not imply that the limit of an does not exist. Okay, don't forget that. So if the sequence satisfies both conditions, bounded and monotonic, then the limit exists. But if one of the conditions is not satisfied, that does not mean the limit does not exist. All right, the last example, f of x is equal to x squared over x plus 1. Again, you can find derivative. This is equal to 2x, x plus 1 minus x squared over x plus 1 square. So you have in here 2x squared plus 2x minus x squared over x plus 1 square, and that is x squared plus 2x over x plus 1 square. This is always positive for x greater than 0. So the function is monotonic, right? This guy, you have monotonic. But this limit, this sequence is not bounded. Again, not bounded. It's obvious because on the top you have square, and in the bottom you have, just linear function. And the limit of this guy we know n squared over n plus 1 and approaches infinity equal to infinity, right? So limit does not exist in the sense that finite limit does not exist. Okay, so I think I stop my video in here. So I hope that all examples are clear enough. And I repeat again, this is some foundation for the next sections when we study sequences. So please watch the video carefully and do homework. Okay, see you in the next video.